Hello. Hi guys, good morning. Welcome back to the new video. Again, in this video, we're gonna see this problem. There's a high chance that many of you have tried something else, maybe graph, maybe BFS, maybe something else too. But we will see for sure the first intuitional step to start this problem off is actually graph. But you will have to figure out that not always graph works, and that for sure we will start off with the graph, we will start off with the BFS, and then we'll figure out okay, it will not work, and then we will have to go on and see the constraints look much less. Maybe we can try something very brute force, and that brute force comes in. So for sure, the recursion and backtracking are the always first step for brute force. So let's see. The problem says minimum moves to spread stones over the grid. Again, we are having a 0 next 2D grid as 3 cross 3 representing the number of stones in each cell. Now, I have just a 3 cross 3 grid that's fixed size, and also that each value in this grid, it can at max be of value 9, which means like in total my grid contains exactly 9 stones. That's fixed for sure. Cool. Now there can be multiple stones in a single cell, which means as you can see that in this cell I have 2 stones, in this cell I have 3 stones, so that there is a possibility that okay, in a single cell they can have multiple stones, but in total in this entire grid I will have 9 stones, and the same goes for this grid, it will have 9 stones. And for sure, as you can see, the entire grid has 9 stones, so one cell, it can have at max of a 9 as a maximum value. Cool. So when that is done, and also the picture, in one move I can move a single stone from its current cell to any other cell if the two cells share a side, which means that okay, if I have 2 stones here, this and this, so I can move this stone here. Now again, it already had 1 stone, right? It already had 1 stone. It had just 2 stones. I moved the stone in one step to the next side, again to the next side, again to the next side. So here I have now got 1 stone, and that's my prime purpose, that okay, minimum number of moves, again that's a condition, minimum number of moves required to place 1 stone in each cell. Ultimately I had just 1 cell which had no stones, and my condition was just to bring that cell to 1 stone. So for sure, I brought it in 1, 2, and 3 moves. So answer is minimum number of moves. Answer is 3. Again, for this particular case, I had 3 stones here. I know I have 0 stones. So basically, my prime condition is to put in a stone here, here, and here. Right. So that's 4 points where I have to actually put in my stones. For sure, it's very normal from the visual. Again, from the visible eyes, it's possible to see, okay, I can just move 1 stone here, and here it will be 1 stone. So for sure, let's name it as numbers. So 1 stone will be here, 1 will be here, 1 will be here. Number of moves is 1 move for this, 1 move for this. So exactly 2 moves, and these 2 places are done. Again, for this location, 1 move I will just move here, 1 move I will move here. Again, for 2 moves, again all the places are done. My answer is 4, which is the minimum number of moves. Aryan, what if you would have moved this stone, which means rather than placing this stone right here, I am, let's say, placing the stone right here from here and then here. So you saw, then for sure it needs also a stone. So rather than being placing here, it will be placing from here to here. So rather than 4 moves, it would have 6 moves, right? 6 moves. And that's the condition. I want minimum number of moves. So, and as we can see, okay, it's a grid and we have some zeros. So multi-source BFS, all that stuff comes in a mind. For sure, it will come in a mind because that is how we are hardwired to look at it. But if we will take, and again, we can start off and I can say, okay, Aryan, what I'm thinking right now is that I will have 3 stones here, 1, 2, and 3. Now, what I will do is I will go on to every of those stones which are having more value than 3. And firstly, what I will do is, again, I'm just speaking out loud of what we are thinking right now, that what can happen and what is the most intuitional way to actually start off this problem. That the first condition which comes in mind is, okay, I have 3 stones and I want the minimum number of moves. So for this particular 3 stones, which means for a particular cell which has more than 1 stone, I will go and try, okay, for any nearest location, go and place the stone here. Okay, for him, the nearest location are 2. this one and this one. So please go and place stone here, because I'm just saying I am only counting the distance of one. So in step one, what I am doing in step one, what I am doing is, for every stone, for every cell having stones more than equal to 0, I'm going on to every of those cells, which means I'll go on to, in step one, I'll go on to every cell having stones more than 0, and for that cell, every of those distance of 1, I will go and place stone there. Okay, for this cell, I'll go and place a stone here. That's done. For this cell, I'll again go and place a stone here. That's done. Cool. But I'm saying for every, in step one, I'll go on for every stone having value more than, like, having a cell having more than 1 stones. So for this also, in for distance 1, I'm only concerned about placing at distance 1 only. Cool. I'll just go and place a stone here. I'll go and place a stone here. Although in step 1 itself, this problem is done. But what is the next step? What I would have done is, in step 2, I will again go on to all of those remaining stones, all of those remaining cells having number of stones more than 1, and then I will go and check for distance 2. Then for step 3, I'll go and check for the distance 3 for all those cells having stones more than equal to 1. And that's how I can just keep on repeating. And that looks more of very feasible, simple doing a multi-source BFS and reaching on to all the stones. And at every point, we are just greedily assigning because of the distance, because I'm just concerned, okay, for this particular cell, I'll just go and greedily assign the shortest distance and we'll solve this problem by that. But we can apply greedy only when it is not dependent on any other stone, which means if I am placing a stone here, was it dependent upon that if I am using the stone 3 or not? No, right? But this was this example. If we just go back to this particular example, then for sure you can easily see that, okay, this will have, it will just simply go on and try to reach this location, this. So it's just a simple one stone. But now we saw that it's a BFS, a simple multi-source BFS, and also for sure it's a greedy because I'm just going on in the increasing distance order. But the main part is it possible or not? For that, let's find out if it is possible or not. So let's say I have one cell and I have another cell. Let's say this cell has 2 stones, right? And when I say question mark, I mean, okay, it's a cell which needs a stone. So it's a question mark, it's a question mark, it's a question mark, and also it is a question mark. Also, let's say it is a question mark. So now you can see that, okay, I have a cell with 2 stones, and let me place it more on the side, and I have these 4 or let's say 5 as the stones in this cell. So again, if I have, again, as I showed you in this particular approach, in the greedy BFS approach, what we will do is we will start off with every cell having stones more than 0. So for this cell, I have stones more than 0. So again, I can go and remove only 1 stone, although it has 2 nearest locations, but still I can go and remove only 1 stone. But that's a fact. If I remove 1 stone, where shall I put it? Shall I put it here or shall I put it here? Now you will say, Aryan, it won't matter. You can put it anywhere. No, it will matter. Why it will matter? Because if you put this stone here, the stone which was here, if you go and put it here, let's make it as have the same color as green. What will happen is you will need 1 step because now what will happen is this cell will go and make 1 stone reach here, so it needs 1 move for this, 2 moves for this, 1 2 3 4 and 5 moves for this stone at this cell to reach this particular place. But instead, contrary, what we could have done was we could have moved 1 stone here, then these number of steps would have reduced, and only you can see to 2 steps would have been reduced if we would have used this approach. So placing a stone, which means I had stone, now placing it on which side of my particular matrix or grid is beneficial, because now placing a stone here was dependent upon that, okay, I have somewhere on the top so that it will have a shorter path to this location. And if, let's say, if this was not have been there, if I had at the bottom, so for sure if I had the bottom many stones, then it would have been much beneficial to actually place in a stone at the left location rather than at the bottom location, and from the bottom it can come in at this bottom location of this cell. So greedy would not work when you are dependent on someone else. Now you cannot blindly go and greedily follow, okay, what's the approach, and what's the nearest cell I can just put my that stuff on, these stones on. So which means that I cannot go and blindly choose any location to place. I will have to go and try for every location, or maybe some specific location, to place my particular stone on. Now the concept came on, okay, I need a specific location to place my specific stones on, and that specific location or that specific order, which means, okay, I place a stone from this cell here, from this cell I'm placing a stone here, 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 and here. Now this specific order of, okay, or the locations of, okay, from this cell I am moving a stone to here, from this cell I'm moving a stone to here, here, here. So this particular stuff, it's required. Greedy would not work, we have got to know. Now we want the specific order of what stones to put in, where to put in, all that stuff. So what can we do? Do we need some specific algorithm for that? Do we need? Let's see. The constraints, as we showed above, it's just a 3x3 matrix. It's not a big matrix. Maybe if we want to try on every possibility, why not we can just go brute force? Maybe, I'm again saying, maybe the complexity, again, the constraints are pretty low, so maybe the complexity is pretty less, or maybe it can be pretty high because it's a brute force, so it can go very high also because it's exponential. But considering it's just a 3x3 matrix, so what even exponential can go off, it might not go that big. So let's try for the brute force. Now again, for the brute force, what we primarily need is this thing. I'll just simply erase this so that for a better view. For brute force, what I'm simply doing is, I know a cell C1, I know a cell C2. I'm not referring these cells as my C cells because I cannot even touch those cells. I can only touch the cells having at least some more stones than one. And let's say these are the 0 cells, which is Z1, Z2, Z3, and Z4. Now I have some 0 cells. Now my main target is, I am starting with, let's say, this Z1 cell, and again, for sure, I'm just referring, okay, I'm starting with this Z1 cell. My task is ultimately to just assign or have an order, okay, for a cell Z1, it can just take a stone from C1 or it can take a stone from C2. Anyway, it's possible. But I want to do it for every of those Z cells, which means 0 cells. Again, for this, I can, from Z1, for Z1 cell, I can get a stone from C1, right? And then what I can do is, okay, when the Z1 cell is done, I can again go to a cell Z2. Again, I'm referring this as, okay, what the order can be. I can go at the cell Z2 and say, okay, you can get the stone from cell maybe C1. Again, for this cell Z1, you can also could have started with getting it from cell C2. Then for your cell Z2, you could have also got it. Again, it can have multiple options. Here also you have a cell C2 as an option. Here also you have a cell C2 as an option. That is how your entire, you saw, if you start off with some specific cell, 0 cell, you can get a stone from cell C1. And then you can just, okay, if I got the cell from the stone C1, I can just decrease the count of a C1 by 1. Now I can just pass on, and I know I have to fill on all the 0 cells. So I will just go on and try for a cell Z2. Z2, it can still have from C1 and it can also have from C2, because here the C1 was 3. Here the C1 have reduced to 2. Because ultimately C1 was 3 here, but when C1 is used, it is reduced to 2 here. Now 2 are here, 1 Z2 will use for him. Again, for C2, here are 3 options. When, let's say, it is done, and again, I'm trying to use a C1, I'll go and have it try on Z3. For Z3, can I use a C1? No, because 1 is already used by Z2, 1 is already used by Z1. So for Z3, I cannot have no options. So I have to for sure try a C2 itself. But you saw what's happening. The entire tree is being built, and the entire, again, recursion, it's not that easy to understand. So please make sure that you understand everything very carefully. I have a cell Z1, Z2, Z3, and Z4, and I'll repeat the same process for every cell, which means here I started off with a cell Z1, and then I will have to go at the cell Z2, and so on and so forth. But when I say start off, I actually mean I assigned either C2 or C1 first to actually cell Z1. Maybe if I don't, and again, you can also memorize this stuff, but that would not be required. I'll show you why, because the complexity is pretty less. But again, the prime fact was I have to go on to every of these zero cells, and as I go on to any one of these zero cells, I have multiple options, or you can say k options. And k, when I mean these cells having more than one stones. I have these k options to actually get my stuff done. And if I use it, okay, let's say if I use a C1 cell for it, I can just reduce the count of number of stones, and I can just go and say, okay, hey bro, for you started off with Z1, you use 1, okay, go and try for Z2, okay, then go and try for Z3, then go and try for Z4. Now it is in this particular order it is going on. But again, here I started off with a cell Z1. Again, I can just repeat the same process. I can start with a cell Z2. I can just say, okay, what if I just try using a cell C1? Or if not, then I can just try using a cell C2. And then again, the same process will go on. Again, it is an entire simple recursion tree which will be built. Now, just to actually show you this recursion tree being built, I will just plot in some Z2, Z3, Z4 up till Zn's. Right? It's just, again, at max you have just 9 cells. From those 9 cells, I will have Z cells and C cells. Again, you know what is a Z cell. Z cell is a cell having value 0, and C cell is a cell having value more than 1. Now, again, I have only 9 cells. So Z plus C is actually a 9. Again, remember this fact. That's prime, most important fact. N, I'm just referring here, but still, N, it cannot be very big. That's a prime condition. And what I'm repeating for a cell Z1, the same will go and repeat for Z2, Z3, and up till Zn. Everyone will repeat the same process, which means everyone will try off with everything, right? So again, for a Z1 cell, I can have multiple options to start off from, which means I can take, for the cell Z1, I can take the value from C1, C2, I can take up till Cn. Now, let's change the color. When I have taken for Z1, now comes the chance. Let's say I have taken for Z1, I have taken a stone from C1. I will go and try for Z2. Again, for Z2, again, I will have all these options, C1, C2, up till Cn. Again, when I say options, please make sure that you reduce the value of C1. And option can only be there when the C1 value is more than 1. Cool. And again, I had a Z3. So let's say, and when I say, it will repeat the same process, which means for Cn also, I can have and say, I can start off with Z2. And again, for this, it will have options as C1, C2, up till Cn. Again, the tree will not stop on, which means I have chosen for a cell Z1. Now I am choosing for a cell Z2. Again, I'm choosing for a cell Z3. For Z3, again, I will have many options, C1, C2, up till Cn. And the same will go for this also. And it will again go for every of those parts. So you see that it's a kind of a recursion tree being built with the height or the depth of size n. When I say n, I mean just for every cell, right? For every cell Z1, you are doing it. For Z2, you are doing it. For Z3, you are doing it. And you will keep on doing it up till Zn, which means you have Zn cells. So you will keep on doing it. But you know that the tree width is dependent upon the number of branches. The number of branches we have is, again, it is for reference of Zn and it is for reference of Cn, which means the number of, or I should say Zn and Cn, right? It is just the breadth of my entire recursive tree. Now you will say, Aryan, with this, the complexity seems like to be Zn raised to the power Cn. Yeah, and that's evident. And you can say that, okay, you have 9 cells, so 9 raised to the power 9. It's pretty big, Aryan. That would not work. Yeah, true, that would not work. But who said that Zn raised to the power Cn is 9 raised to the power 9? I told you that Zn plus Cn is equal to 9. And when we want, okay, some value is equal to 9, we want, okay, its highest value. So we just break down in the mid. So 4 plus 5 equal to 9, or 5 plus 4 equal to 9. So basically 4 raised to the power 4 raised to the power 5 or 5 raised to the power 4 would be the maximum value of my entire recursive tree. It is around 1k. So now you required your entire recursion which you are building, and for sure you are trying every possibilities. For cell Z1, you are trying to choose a stone from C1, C2, C3 up till Cn, which means you are trying every cell for this particular stone. Again, when you have chosen a stone for Z2, again you are trying on for every possibility, and it will keep on repeating, which means for Z2 also you will try on and try for every possibilities. Then from Z2 you can just go on to say, let's say Z1, and you can try on for every possibility. But you see that, okay, for every stone, every Z stone, I'm going and trying on for every possibilities. For every Z stone, I'm going and trying for every possibilities. And with this factor itself, again, when you are using for Z1, and for sure you will be using some stone, so it will be used either C1, C2 up to Cn, it will be used. Any one stone will for sure be used. So the recursion tree being built, and I will keep on counting the number of steps required and how the steps are required simply by getting the coordinates. If I have a C1, I have a Z4. If I'm saying, okay, for a cell Z4, I'm using a stone from C1, so I can just know, okay, what's the coordinate of C1, what's the coordinate of Z4, and with the coordinate difference, I can just find out the distance between them, which is the Euclidean distance. And with that distance, I can just go and find what is the count required, and I can just go and find the count for my entire recursion tree, and I can just take the minimum of all these count which I have got from the leaf nodes, and that's how you can simply get this solved. Again, the complexity is pretty low, although it can be like this 4 raised to the power 5 into some n square stuff, but that I can just do a pre-computation, as I showed you that for every C cells I need a for every, basically I just need all these C cells and I need all the Z cells. So I can just do a pre-computation and get all the Z cells together and all the C cells together. And with this pre-computation itself, it would be very easy for me just to go and start my entire recursion from the Z cell, which means I will have an I pointer at these Z cells, and for every of these Z cells I go and try for all the K cells. And when I say K, I mean K C cells, right? I'll go and try for all the K C cells, and I'll go and repeat this until my all these Z cells are finished, which means until my I is greater than or equal to Z dot size. When I say Z, I mean 0, and when I say C, I mean, in my code I will be referring extra, which is the cells having extra ones. Cool. Now I'll just say, okay, if this has reached, which means you have entirely done with all the 0 cells, you are good to go. Just go and refer me what is the count at this current point of time, and that count will be my actual count as the answer. Again, you can just have a simple memorization also, because you know that your recursive state will have I and count, because you are moving on to all the 0 cells, so you will have a I, you will have a count. But again, you saw that the recursion itself is more than sufficient because it's very less in complexity itself. Cool. Let's quickly have look at the code again. As I showed you, I will need to have a pre-computation of my 0 cells, and when I say 0, I actually mean the coordinates also, and also the extra cells. And when I say extra cells, I need the coordinates plus the actual value which I can deliver to my 0 cells, because one extra cell, it can have a value 4, which means it can deliver 3 extra ones. So I'll just go on entire grid of 3 cross 3. I'll just say, okay, if it's a 0 value, so it's a 0 cell, so push the coordinates in my 0 vector. Else, if it's a 1 value, which means if it's a more than one value. So simply push this in my extra vector, pushing the coordinates and also the number of extra ones I can deliver next to my next person. And for sure, if the zero cells are zero, so for sure no number of steps would be required, so return a zero. Else you have an answer as int max. You will just try to minimize that answer because you want the minimum number of moves. Starting off with the first index, which is the I will have a 0 and I will have a count with me. As I have a 0, which means indexing is from 0, because I will go and have to try to fill every of these 0 cells, right? So I'll go and try for every of these 0 cells, and for sure initially my count is 0. Again, as I showed you in the base case itself, if I have used and completed all my 0 cells, which means my I is more than equal to my 0 dot size, which means I have evaluated all my 0 cells, I am good, very good to go. I'll just get, okay, what's the minimum of whatever minimum, because it's a global variable, as I showed you. I'll get all the counts. Out of all the counts, I just need the minimum count. I'll just need the minimum count. So whatever minimum value I have, okay, the current value and the whatsoever I have the count, just get that done. Now for every of these 0 cell, go and try for every of the extra cell, which is the C cell. So I just go and try for every of the extra cell. Now again, if this extra cell value is actually a 0, which means I don't have any 1 to deliver you, so please continue it. If not, then I can use one of the ones. It just, for this particular cell, extra cell, it is storing number of ones it can deliver. Just simply keep one of the ones, and if you just give one of the ones to the next person, so next I will evaluate for the next 0 cell with the new count. Now new count is the number of moves to reach from that extra cell to a 0 cell, so that's nothing but subtraction of their x coordinates and subtraction of their y coordinates and the existing count whatsoever I have, because I am just carry forwarding that existing count plus the new count, and new count is from here x extra cell to a 0 cell whatsoever number of distance is there. So that is done. I'll go and try to solve it now, but you know that, okay, you have to try on for all the counts, right? Which means that for a specific 0 cell, if you go and try for the count C1, which means for C1 you are using. Now when you go and try for the count C2, which means starting from the Z1, you are going and trying for the C2 count. Again, it will go on to, let's say, Z2, and for that it will try on for C1, C2 up till Cn. If you have used a C2, although if in a recursion you will start from a cell Z1, which is I equal to 0, for that you will go on to all of these K extra cells. You use this K extra cell, right? As you saw, you reduce its value, but you saw that, okay, after the entire recursion of this particular is done, it will just again come up. And when I say again come up, it will go on to the next K. It is K equal to 0. It is K equal to 1. It will go on to next K. Now, as the recursion has entirely been done for this particular stuff, this particular tree, the entire recursion is done. When it is coming up, and then going on to next K, you have to again make the count of C1 back, which means if you had reduced the count of that particular extra cell, then please, after the entire recursion is done, when you are coming up as in back, please increase the count back, because now you are now decreasing the count. In the next iteration, you will now decrease the count of C2, and C1 count will remain intact. So in the next iteration count, again the count will decrease, but the previous count, it should remain intact. And that's the reason when the recursion is done, please increase the count back. And that's the entire concept of recursion. Although there are again multiple ways to implement this recursion, but still, and we have discussed this entire stuff. If you have not watched the backtracking entire 1 hour video, you can just go and check that. But that is the entire backtracking part which you need to know. And it's just a simple recursion. Just saying, after the recursion is done, just simply put that value back, and before starting the recursion, as you're using that value, so please reduce that value. And complexity, again, I have explained above also, that's not much. Zn raised to the power Cn. Again, for this entire concept, into you can just have a bit of n as well for just iteration and stuff, but that would again not be that much. And this value's maximum is 1k. As we know that zn plus cn is actually a 9, and that's to refer a maximum value. It will be roughly 4 power 5, or it can be a 5 power 4, but we see that this is a higher value. So this value will come in here and you will just have it in. Again, you can also be using a O of n square with it. Still, it would have worked because it has a greater bandwidth to actually expand its complexity. I hope that you guys got the entire intuition why BFS is not used, why greedy is, what means by greedy in this, and why is that not being used, what is actually being used in this particular problem, how we are solving it, how the entire recursion tree is being made, how the complexity is being determined, and how we are solving this problem, and with the code itself. Again, I'm showing the code. That's pretty much it. I hope that you guys got it. See you until, goodbye, take care, bye bye.